Hey guys, today we're in chapter 1.3. We're going to start finding limits. Rather than looking at a graph, we're going to look at things analytically. So find the following limits if they exist. If the limit does not exist, give a reason. I was doing that on the first homework, like I was saying unbounded, or the left side doesn't match the right side of the limit, etc. So there are definite steps for what you should be trying. So the first is to pen out here. The first step is to try direct substitution. Direct substitution is exactly what it sounds like. If you're supposed to find the limit as x approaches 2 of f of x, plug 2 into f of x and see what you get. As long as it doesn't come out as an undefined value, you'll be able to figure out the limit, whether it exists or not, and so forth. And if we have a piecewise function, we plug 2 into both the left and the right side. So direct substitution, left and right, if you have a piecewise function. And so what we're looking for is that the limit as we approach x from the left is the same value as the limit as we approach x from the right. So starting on, let's see, these are x values greater than 2. So this is like 2, 3, 4, 5. So this first part would be we're approaching 2 from the right because these are all values to the right of 2. So the limit as x approaches 2 from the right of x plus 1. I like to write the equation if I can, if it's not too complicated, rather than just f of x. What does that limit equal? Well, again, you're just plugging in 2. So 2 plus 1 is 3. So the limit on the right side of 2 is 3. We also need to check the limit as x approaches 2 from the left. Now, the second piece of the function, x value is less than 2. So that's like 1, 0, negative 1. So you would be coming up on 2 from the left if you're on this piece. So that function is 2x minus 1. When you do 2 times 2 minus 1, 4 minus 1 is 3. Since the right-handed limit and the left-handed limit are the same thing, this limit exists, and it's 3. So, therefore, these 3 little dots in a triangle, that's a mathematical symbol for therefore. So, therefore, the limit as x approaches 2 of f of x is equal to 3. You need your limit notation, and it's important to show this work and write things out. Okay, number 2. G of x is this piecewise function. It's 3x minus 1 when x is not equal to 5, but when x equals 5, g of x is 2. So find the limit as x approaches 5. Well, remember, the limit as x approaches 5 has nothing to do with the actual function value at 5. It's just, are we getting the same thing from both sides? The equation is 3x minus 1 no matter what, whether you're coming from the left or the right. And so I can use direct substitution to find this limit just by plugging into 3 times plug in 5 minus 1. 15 minus 1 is 14. So the limit as this function approaches 5 is 14. The actual function, g of 5, is 2. But again, this would be like a graph that looks like this, has a hole, and then the actual point is down here. And if you're having trouble figuring out limits, it does help to graph them or think about their graphs, even if they are piecewise. Find the limit as x approaches negative 4 of f of x. Be careful of your notation. It's easy to read this as 4 from the left because of our signs and stuff. Remember, the plus and the minus are kind of in that exponent position. All right, so the limit as x approaches negative 4. We have 2 pieces to this. We want to make sure we get the right side limit to the correct equation. So as x approaches negative 4, this top equation, if it's greater than, you're approaching from the right, because these are values that are to the right of negative 4. So put a little plus sign up there. Limit as x approaches negative 4 from the right of negative 2. Negative 4 minus 2, negative 6. Check the left-handed limit. The limit as x approaches negative 4 from the left of 2x, so we're on this equation, 2 times negative 4 is negative 8. those limits do not match. If we were to have this graph, it would be like, let's see, it's got some sort of a slope right here. And then it picks up to a different spot. I'm not paying attention to where the points actually are, but it would be something like this, where the limits do not match. So this limit does not exist. What's the reason why? This is the one that is kind of annoying to have to write out, but you're basically just writing out the limit, and you would need to use this math notation. The limit as x approaches -4 on the right of f of x does not equal the limit as x approaches -4 from the left of f of x. And you can flip-flop which side you put on which of that inequality, that's fine. All right, what about number 4? We always try direct substitution, but if I try direct substitution, I'm going to call that ds, by the way. Direct substitution doesn't work. Why not? Because if you try it, you get 1 plus 3 is 4, divided by 1 minus 1 is 0. Remember, that's undefined. So think about what's happening, because we need a reason why this limit doesn't exist. And when direct substitution fails, sometimes we'll have ways to rework the problem to see if it actually does work. So think about this graph. That's sort of your next step if direct substitution fails. We should be able to think about this graph, x plus 3 over x minus 1. We know it's rational. It's got a vertical asymptote at 1. You don't really have to plot points, but you could be plotting points. Like if I plug in 0 for x, I get -3. It's got a horizontal asymptote. I really don't need to go into all of this detail, but just try to picture your standard rational function graph with one vertical asymptote. It's unbounded. So the limit as x approaches 1 doesn't exist because the graph is unbounded. On either side, it goes to either negative infinity or positive infinity. So it does not exist, and I'm just going to write unbounded. How about unbounded at x equals 1? What about the limit as x approaches 2 of the absolute value of x minus 2? So remember, try direct substitution first. Direct substitution is just plugging 2 in. Absolute value of 2 minus 2 is 0. That's a valid number. A limit can be 0. Think about that graph. That's the absolute value graph shifted to the right 2 units. So yeah, that limit is 0. Limit exists. Its value is 0. We're going to see this type of equation a few times in this chapter. So where you have the same expression, numerator, denominator, but one has an absolute value. So basically this divides out to either 1 or -1. And so you should be able to quickly look at this after you've seen it a few times and say, oh, this limit does not exist. You can graph it to be sure, but 2 is the breaking point, right? 2 is not defined. But if I plug in like 3, I get +1. If I plug in 4, I get +1, 5, +1. If I plug in 0, I get -1. So, well, I guess I should have said, if I plug in anything less than 2, then I get -1. And so again, as we approach 2, right here, the limit doesn't exist because the left side of the limit doesn't match the right side. So limit as x approaches 2 from the left. This doesn't say f of x, so I can't throw an f of x in there. I would have to write the equation. And it's wrong to just put the limit notation without a function following it. So it all seems, the math right now is not hard, but it's more the notation and what you have to write and not forgetting those things. All right, so number 6, that limit does not exist. More of the same. Find the limit if it exists. If it doesn't, give a reason why. So again, we have another piecewise function. So I'm going to use direct substitution on the left and the right. So the limit, let's do this right here. The limit as x approaches 1 from the right of x plus 5. 1 plus 5 is 6. And the limit as x approaches 1 from the left, bottom equation of 6x also equals 6. So therefore, I'm trying to save myself a bit of writing here. This overall limit is equal to 6. For number 2, approaching -2, so the limit, actually, be smarter about where I put my work. I'm going to write my answer here if it exists, so let's do our work below. The limit as x approaches -2, this time it's from the left for the top equation of 4x. 4 times -2 is -8. The limit as x approaches -2 from the right of the bottom equation, 3x minus 1. -6 minus 1 is -7, so that limit does not exist because the limit as x approaches -2 on the left of this function is called g of x is not equal to the limit as x approaches -2 from the right of g of x. Okay, number 3. And you want to keep writing this notation. I know these are just notes, but if you don't get in the habit of writing it now, you're going to forget on the quiz, and that'll just be point after point after point that gets docked if you don't have the correct notation. Okay, limit as x approaches 3. When I have an x not equal to 3, this top equation represents coming at both sides. So I use direct substitution right away, and I don't care about the function value at all. I can ignore that. So I can say direct substitution, 3 or -3. These two restrictions say -3, so let's make that a -3. That's probably just a typo, if you can have a typo. Anyway, plugging in -3, -3 plus 4 is 1. Number 4 has 3 parts to it, so limit as x approaches 2. Again, we don't care about the actual function value. I can ignore the middle piece. I just care about the right and left side and what's going on. So the limit as x approaches 2 from the right is the top equation of 2x minus 1. Direct substitution, 2 times 2 is 4, minus 1 is 3. Plug into the bottom equation the limit as x approaches 2 from the left of 3 halves times x. 3 over 2 times 2 is 3. Since those two sides match, the overall limit as x approaches 2 of f of x is 3. Limit as x approaches 2. We have a rational expression. 2 is the vertical asymptote, so I shouldn't really have to do any work or show anything. I can just say this limit does not exist, unbounded at x equals 2. I guess it'd probably be good to say f of x is unbounded at x equals 2. What if we have the same function, but we're saying the limit as x approaches 3? Here, direct substitution does not fail, so we're not unbounded at 3. We plug in 3 and get 7 over 1, so that limit is 7. Number 7, we saw this function before. An absolute value of an expression divided by that expression is always going to be 1 or -1, and as x approaches 1, that's the breaking point. That's where you get 0 over 0. It's undefined at that place. So this does not exist because the limit on the left doesn't match the limit on the right. So the limit as x approaches 1 on the left there's no f of x, so let's write out the function equation. Is not equal to the limit as x approaches 1 on the right, that function. Now, if we don't have an absolute value, now we're saying at 1, this is 0 over 0. I can simplify this, though, right? Like, think about this graph. If I told you to graph this, x minus 1 over x minus 1, it does reduce, doesn't it? We can say that reduces to 1, but x can't equal 1. So if you're thinking about this, you have this graph that's just a horizontal line, and then when you hit 1, there's a hole in the graph, and then it continues on. So what is the limit as x approaches 1 of a function that's just 1, it doesn't matter that it's undefined there. The actual limit is 1. Okay, then we get into a little bit of trig here. So what's the limit as x approaches pi over 2, tangent of x? There's all kinds of things you could do to think about this. The graph of tangent x, all those fun speed quizzes you had to take in honors pre-calc, tridirect substitution, tangent of pi over 2. Remember, tangent is y over x, pi over 2, top of the circle. I hope you don't have to think this much about it, but y over x would be undefined. Okay, what's happening at the tangent graph? Remember, the tangent graph has vertical asymptotes at pi over 2 and negative pi over 2, and it had kind of this curve going on. So this graph is unbounded because to the left of pi over 2, you're going to infinity, and to the right of pi over 2, negative infinity. So does not exist. Tangent x is unbounded at pi over 2. The limit as x approaches 0 of tangent x. Now, you can see my graph here. At 0, we can plug 0 into tangent x and get a value at 0. Or think about your unit circle. Y over x for tangent would be 0 over 1. That comes out to a value. So that limit does exist, and it's 0. Here's a problem you might see. Probably in a multiple choice that you'd have to do a bunch of little side work on. So given that f of x is this function, notice there are two unknowns, a and x. Find a if the limit exists. So what does it mean that the limit exists? It means that the limit on the right side has to equal the limit on the left side. So I can say the limit as x approaches 3 on the, I guess I'm going to start with right because that's the top equation. On the right, ax minus 2 has to equal the limit as x approaches 3 on the left using 3x plus 1. So if I know that to be true, I can use direct substitution. You're putting 3 in for x. So on the left side, it would become a times 3, or let's make that 3a minus 2. On the right side, 3 times 3 is 9, plus 1 is 10. And then I can solve for a with just some algebra here. So a comes out to be 4. Using the fact that the limit exists, we can set up that equation. All right, for number 2, given this g of x, it's got 3 parts to it, find a if the limit exists. So again, we're ignoring the function value part and just looking at the right and left side equations. So the limit, then I can't just jump right to direct substitution. If I'm doing this on you could if you're doing a multiple choice question, but if this is part of a free response or like something on one of my tests, I want to see that you're using the fact that this limit exists. You're showing what you're setting up. So don't skip to just, negative 12 plus a equals negative 4a. Don't skip to that. Show this part. Limit as x approaches negative 4 from the left of 3x plus a has to equal the limit as x approaches negative 4 from the right of ax. And then we can use from this point, we can use direct substitution, plug in negative 4 for x. So that would give me negative 12 plus a equals negative 4a. I can solve for a. I'm getting 12 over 5. All right, so that's my value of a. Part B says, at the value of a that you found in part A, does the limit as x approaches negative 4 of g of x equal g of negative 4? So the value of a is not the limit value. It's just the missing piece to that equation. So now we have to find the limit. You don't have to plug it into both sides because it's been established that you're going to get the same answer no matter what. So I'm going to plug into the bottom equation because that seems easier. The limit as x approaches -4 of, instead of ax, I now know that it's 12/5 times x. That would be -48/5. So that's the limit value. G of -4, that's the middle piece of the equation. When x equals -4, you use the equation x plus 2. That would be -4 plus 2, which is -2. So does this limit equal this? Make sure in the AP test, like this is not, I'm not finished at this point. My answer would be no. Limit as x approaches -4 of g of x is not equal to g of -4. So don't forget to actually answer the question. Or you could say, like back here, I guess I could have also said like no, comma, and then shown that work. All right, we also need to do day 2, since we got off to kind of a slow start in the beginning of the year. So you might be finishing for homework at this point or continuing on. But this is technically our day 2. So we're still saying, okay, we don't care about the actual function value of f at x equals c, but the limit as x approaches c of f of x is just dependent upon the left and right side behavior. So sometimes it's the same as f of c and sometimes it's not. We've been using direct substitution. As long as direct substitution is defined, then we've been using that to find function values. Well-behaved functions for which the limit actually is the same as the function value, those are called continuous, and we're going to talk about that more, I think, Monday, if I'm getting my days straight. There are some properties of limits to talk about. They kind of make sense. So these are just kind of some basic properties. The limit as x approaches c of b, if b is a constant, b and c are real numbers, is b. So like the limit as x approaches 2 of 5 is 5, because 5 is just, the function is just a horizontal line. That's the limit everywhere. The limit as x approaches c of x equals c. Again, direct substitution would just tell you to plug that in and call it a day. So this one, next one should be -4. And if you have an exponent on there, again, direct substitution says you can just sub that right in. So the limit as x approaches 8 of x squared is 8 squared, which is 64. You can also work with multiple limits and multiples of limits. So like our first one is a scalar multiple. If I'm taking the limit as x approaches c of a function, and there's some scalar multiple, some constant out in front of the function, if it's easier, I am allowed to pull that out in front like this, take the limit as x approaches c of the function first, so direct substitution, and then whatever that answer is, multiply it by b. You're allowed to add or subtract two functions together and then take their limit, or it's often easier to separate them, take the limit of f and add or subtract that to the limit of g. Same thing with multiplication. Same thing with division, assuming your denominator doesn't equal 0. And same thing with an exponent. If it's easier to take the limit before you raise your answer to an exponent, then you can do that. Take the limit of f of x, get that number, then raise it to whatever n is. We did that on this one, right? Plug in the limit as x approaches 8 of x squared. We plugged in the 8 for the x, and then we squared that answer. That's kind of what that's saying. All right, so we've been using direct substitution, but now we're going to have some more complicated functions. So direct substitution should work for polynomials, radicals, rationals, trig functions, as long as the value you're plugging in is in the domain, meaning it can be plugged in. And if it can't, we'll explore a few workarounds. So the limit as x approaches 1 of this function, let's just do direct substitution. 1 squared plus 1 plus 2 over 1 plus 1. So that's what? 4 divided by 2 is 2. Direct substitution works. Here, if I plug in 1, I get square root of 1 plus 4 is 5. That's a number. It's fine. This one, I can plug in pi times cosine of pi. Think about your speed quiz days. Cosine of pi should come quickly. It's -1, so this becomes negative pi. That's a valid answer. And we did this on the previous page. At 2, we're undefined. You get 0 divided by 0. 0 divided by 0 is not equal to 0, and it's not equal to 1. But remember, this can reduce. And so you can say, really, we're looking at the limit as x approaches 2 of just this reduces to 1. That's a constant function, and your answer is 1. The function's undefined at 2. There's a hole, but otherwise it's 1 everywhere else. Functions that agree at all but one point. So there's basically a dividing out, or what we just did. You can simplify a rational function. If that helps you, then use direct substitution. So if I have something like this example, x cubed minus 1 over x minus 1. Direct substitution fails because when I plug in 1, I get 0 over 0. That's your hint. It's a red flag. You need to rewrite the problem. When you're rewriting, keep your limit notation in your work until you actually use direct substitution to take a limit. So we need to factor out, using our difference of cubes, our SOAP formula, x cubed minus 1. And then that shows us that the x minus 1's cancel. And so when I do direct substitution, which is my next step, I'm only subbing into x squared plus x plus 1. 1 plus 1 plus 1 is 3. The rationalizing technique. So you're used to rationalizing the denominator, but in this case, we're going to have to rationalize the numerator. Why do I have to rationalize the numerator? Because if I plug in 0, I get 1 minus 1 is 0 over 0. So I need to rewrite. All right, well, what do I want to rewrite as? I'm going to erase this. Sorry, so I don't have to copy the problem again. I can multiply by the conjugate. Remember, the conjugate is just this expression with the sign changed between the two terms. Square root of x plus 1 plus 1. When I multiply by the conjugate, I will always multiply out the numerator so that I get rid of the radicals, and I will never multiply or distribute anything through the denominator. Just leave that as is. So don't forget your limit notation. Limit as x approaches 0 of when I FOIL or distribute the numerator, I get x plus 1. And then remember, the conjugate works that these middle terms would cancel out. And then -1 times 1 is minus 1. Over down here, just leave it. It's a lot of writing, but leave it as x times square root of x plus 1 plus 1. Now simplify. So you've got limit as x approaches 0 of, really, this is just x over x times square root of x plus 1 plus 1. These x's are going to cancel, so you'll be left with 1 over square root of x plus 1 plus 1. And at this point, I can do direct substitution, and I don't have to write my limit notation. So when I plug 0 into this, I get 1 over, when you plug 0 here, you get 1 plus 1. So the function value is 1/2. And if you're unsure of that, you can check these for now. You can't do this on test day, but you can check these in your graphing calculator. Plug the original function into your graphing calculator and see what it looks like. Does it look like it's approaching 1/2 at x equals 0? All right, so recap of what we're talking about here. If I have when I'm doing direct substitution, if I get a non-zero divided by a non-zero, I'm just getting the limit, which is equal to whatever that number is. If I have 0 divided by a non-zero, that limit is equal to 0, right? Like 0 over 10 or 0 over 2, whatever. If I have a number divided by 0, that limit does not exist because it's unbounded. That's like, we sub in and get 1 divided by 0. Oh, there's a vertical asymptote there. Continue on. If I get a 0 divided by a 0, that's what we call the indeterminate. I don't know if I used that word yet. Indeterminate case, 0 divided by 0, and you need to rewrite, check direct substitution again. So again, our steps are always try direct substitution first. Sometimes you're checking that in your head if you realize like, oh, that's not going to work. If it's rational, try factoring, canceling things out, and then direct substitution again. And if there's a radical in the numerator, try that rationalizing technique. Okay, this is our last page, I think. Yep, this is our last page for the stand notes. So there's a fun little theorem called the squeeze theorem. Sometimes you'll hear it called the sandwich theorem. But what this is saying is, suppose we have 3 functions, and f of x falls between h of x and g of x. And they may be equal at some point. And that's true for all x in whatever interval we're talking about that contains c, which is the limit value we're approaching. The limit as x approaches c of h of x equals L, and the same thing is true for g of x. So you can see on this graph, g of x is approaching a certain value, and it's the same value that h of x is approaching at that c. As long as it's guaranteed that f of x is sandwiched or squeezed in between those 2 functions on that interval containing c, then we know that the limit as x approaches c of f of x exists, and it is the same thing as the limit for h and g of x. So if you look at this graph, it's kind of hard to speak about it, but if you look at this graph, it's like, oh yeah, they're all zeroing in on the same point. There are 2 special trig limits that you could just memorize. We often use them with the squeeze theorem, but in interest of time, I'm not going to go through the proof. The proof is on page 65 in your textbook if you'd like to look at that. But for now, we're going to memorize these. Eventually, we'll have some work we can do to kind of visualize them. But the limit as x approaches 0 of sine x over x is equal to 1. And again, in interest of time on this video, check the reciprocal of this. If you look on your calculator and type in x over sine x, at 0, are we approaching 1? That answer will be yes. So also, if you see the limit as x approaches 0 of x over sine x, that's also equal to 1. This is only the limit as x approaches 0. So if this were to say the limit as x approaches 5, that answer would not be 1. It would be sine of 5 over 5. But since we can't do direct substitution here, this is one that we'd be using the squeeze theorem on, proof on page 65, and you can see that. The limit as x approaches 0 of 1 minus cosine x over x is equal to 0. Again, that's just something to memorize. If you check the reciprocal, it's not true. So the limit as x approaches 0 of x over 1 minus cosine x, that is not equal to 0. Okay, there's one more thing about this. It's important when you're using these limits that whatever expression is in the angle part of the sine function or the cosine function, that has to match the denominator. And I'll tell you what I mean by that when we get to problem C. So for now, part A, limit as x approaches 0 of sine x over x, no work to be done. It's equal to 1. If we go down to part B, now I have sine squared. I need to rewrite this. Limit as x approaches 0 of sine squared is the same as sine x times sine x. There's still an over x. Okay, so remember when you have multiplication going on in your limits, our properties a couple pages ago told us, oh, I can take the limit of each part individually. So the limit as x approaches 0 of sine x over x, that's 1. The limit as x approaches 0 of sine x, if you're plugging 0 into sine x, sine of 0 is 0. So 1 times 0 is 0. We plug in negative pi over 4 using direct substitution. We would get 0 over 0, 1 minus 1 over negative radical 2 over 2 plus radical 2 over 2. So if it's trig, we've got to rewrite this in some way. And sorry, I don't know why I skipped part C. We'll come back to that. But also if it's trig, we can do a little bit of work here. Tangent is sine x over cosine x. So maybe we can use some of our trig identities from last year to simplify this thing, and then maybe direct substitution will work. So remember, this is a complex expression. I see a denominator of cosine x, so why don't I try to just multiply by cosine x over cosine x? And when I do that, I've got to remember to distribute. And I need to remember to bring along my limit notation, because yes, I'm working algebraically, but I need to keep the limit notation. So this would become cosine x plus sine x in the numerator. And then I don't want to distribute anything through because I'm seeing right now that I would have sine x plus cosine x times a little cosine x down there. These are going to cancel. So I've got the limit as x approaches negative pi over 4 of just 1 over cosine x. Direct substitution does work into that. You get 1 over negative pi over 4 is in quadrant 4. Cosine of pi over 4 in quadrant 4 is positive radical 2 over 2. If you flip that, it's going to flip to radical 2. Because remember, this was, before you rationalized it, it was 1 over radical 2. So if you think about its unrationalized version, it's easier to get the reciprocal of that. Or do 2 over radical 2, simplify and reduce. Back up to C. Okay, so this is what I was saying. Right now, this is not the same as sine x over x. This is sine of 2x over x. I need a 2 right here. I can't just put a 2 in a denominator because now I just cut the whole thing in half. But if I just multiplied a 2 into the denominator, I am allowed to multiply a 2 into the numerator because I just multiplied this function by 2 over 2. That's legal. Multiply by 1. I didn't change anything. And so I can use that property on the previous page that said if there's a constant out in front, you can pull that out, or you can think of this as like, okay, I'm really taking the limit as x approaches 0 of 2 times the limit as x approaches 0 of sine of 2x over 2x. So since these are being multiplied, I can multiply those two limits separately. The limit as x approaches anything of a constant is the constant. And now I have the limit as x approaches 0 of sine of something divided by that same thing. That's equal to 1. So again, this angle has to match the denominator. 2 times 1 is 2. So that's our final value. Okay, up to E. I'm going to get 0 in the denominator when I plug this in. And I'm going to get 0 in the numerator. 0 plus 0 over 0. So again, this needs to be rewritten. Now, right now, if I have x plus cosine of x, or x plus x cosine x, maybe I want to factor an x out. See where that gets me. Okay, that gives me like an x plus cosine x. So now I can look at this separately, because this is something that you may or may not see the first time you look at it, but you have x over sine x. Remember, back here, the reciprocal of that first limit, that's also equal to 1. So I can separate this out. I can say the limit as x approaches 0 of x over sine x. It's being multiplied by the rest of this. So the limit as x approaches 0 of 1 plus cosine x. So this first limit I know is equal to 1, multiplied by, check direct substitution again. Anytime you rewrite, you check direct substitution. 1 plus cosine of 0 is 1, so 1 plus 1 is 2. So that limit for part E is equal to 2. Finally, be careful on F. this answer is not 1, even though I see sine x over x. Its limit as x approaches 3 pi over 2. It's only equal to 1 if you're approaching 0. Direct substitution works here. You get sine of 3 pi over 2, which is negative 1, over 3 pi over 2. We would never leave our answer complex like that. So negative 1 divided by 3 pi over 2 is negative 2 divided by 3 pi. Okay, final example here. Find a and b if the limit as x approaches 2 of f of x and the limit as x approaches negative 1 of f of x both exist. Show work. Okay, so if the limit exists, let's start with 2. Then the limit as x approaches 2 on the right for the top equation of ax plus b needs to equal the limit as x approaches 2 from the left. And where are we approaching 2 from the left? That would be the middle equation. X is less than or equal to 2. So of bx minus 3. Next step is to use direct substitution by plugging in 2 for x. So you get 2a plus b equals 2b minus 3. The only other thing I can do with this is maybe get the b's on the same side. So this could be 2a and then minus b equals negative 3. But I can't solve for either a or b at this point, so I have to pause. And then I go on to my next piece of information. So the limit as x approaches negative 1 of f of x exists. So let's start that. The limit as x approaches negative 1 from the right of bx minus 3 has to equal the limit as x approaches negative 1 from the left of a over 2x minus 2b. Let's plug negative 1 in. So negative b minus 3 equals negative a over 2 minus 2b. I don't like having that negative a over 2, so I'm going to multiply everything by 2, but maybe I'll collect my b's first. So negative 3 equals negative a over 2. If I add b to that, I get negative b. Multiply everything by 2 just to get that out of there. Maybe negative 2, since all these are negatives. I'm going to multiply everything by negative 2. So that becomes 6 equals a plus 2b. Now I have 2 equations and 2 variables. I can set up a little system. I could do substitution. I could do elimination. It does not matter. I think I'm going to take this over here. I think I'm going to just do substitution. I'm going to solve this blue equation for a. That would be 6 minus 2b. I have to be careful because my b's and my 6's look alike. And then I'm going to sub that into the red equation. So 3 times what is now a, 6 minus 2b, minus b equals negative 3. I'm going to solve for b. So I'm getting that b equals positive 3. And then I can go back and find a, because remember this blue equation, a is equal to 6 minus 2 times 3. And so 6 minus 6 is 0. B is 3, a is 0, and that's all we had to do, find a and b. You could have solved the actual system differently. Maybe you found a first. It doesn't matter, as long as you get the same a and b. Okay, things to study. Identify the 3 cases in which a limit does not exist. Okay, so in one case, we have the long one that we don't like writing out. The limit on the left is not equal to the limit on the right. Second case, let's see, maybe if we have a rational function and the limit, the c value that we're approaching is unbounded, so I'm just going to write unbounded. unbounded at x equals c. I'm sorry, how about, that's probably true at x equals c, but let's just be careful, right? As x approaches c. What's the third one? We haven't seen this a lot. We did this maybe a couple of days ago in notes. The last scenario is if your function is oscillating at c. We had a crazy sine function at some point where it was like, everything's fine, and then it went like this, and then like went back. And so at this craziness, there was no function value. Name 3 specific methods of finding a limit analytically. So our first one that we always try is direct substitution. If direct substitution fails, maybe we have a rational function and we can factor or rewrite, like with the trig function, simplify. So we did that with using some trig identities. We did that factoring and canceling. And the third scenario, if you have a radical, is to rationalize the numerator. All right, so those are a couple of things to study before we have a quiz or a test over all this stuff, just to kind of make sure you've got your definitions in place and when does a limit not exist and how do I actually find limits. All right, that's it.